Next, we have the use of coupled surface water groundwater models in managing water resources. Dr. Ron Green with the Southwest Research Institute will bring our next presentation, and I ask that you introduce yourself and let us know what's important.
Hi. Yes, I'm Ron Green, Southwest Research Institute. I'm a groundwater hydrologist, and I appreciate the opportunity to make a presentation at the Texas Alliance of Groundwater Districts Summit and to talk to all these groundwater people about surface water. So we're in Texas. You know, we have surface water here, we have groundwater here, and there the twain shall meet. That's how they address it in Texas. So I'm going to look at a case study that we've recently achieved some advancement and give illustration of some of the attributes that you might be able to appreciate if you incorporate surface water in your groundwater investigations. As was said, I'm a groundwater hydrologist, but as we're finding out these days, it's much more difficult to achieve the goals of managing water resources if you do not take into account both surface water and groundwater. So what I'm going to talk about today is an example of that. It's out in the west central Texas area. It's in the Edwards Plateau. So we see that the Edwards Trinity Aquifer takes up a goodly portion of the state. You know, you can slice and dice the Edwards Trinity any way you want. This is from the GAM, and they've parsed it out into these different sub-segments. But when they model it as a single unity. It's one large system that's being modeled as groundwater. And what we're looking at is problems that you encounter when you try to take a large system like this and draw local analyses out of it. The GAM is very good for what it was intended to do, looking at this large system. It's not so effective when you're looking at some localized impacts. So for that, we've developed a smaller model, and we've used some past work that we've done in order to guide us through this process. So we recently completed an expanded model of the Edwards Aquifer where we included the contributing zone. And up in the contributing zone, you have the Edwards at the surface, but it's unconfined. And underneath that, you obviously have the Trinity. And what we found are that all the contributing watersheds in the contributing zone act as separate entities. That's because it's unconfined, and the water from one watershed does not tend to migrate to another, no matter what happens in one watershed. For example, if you're pumping in the Cibolo watershed, you're not going to be pulling water over from the Guadalupe or other adjoining watersheds. So we took this understanding when we addressed the issue out in the Edwards Plateau. So this is a map that shows the watersheds that contribute, that make up the Edwards Plateau. And a number of these watersheds have their headwaters right up in this central area. So I'm going to focus on the Devils right in this area, and we're going to model that separately. So once again, we're able to do this because the greater portion of this watershed is unconfined, meaning that there's no confining unit over it, and because we're looking at the Edwards Trinity, of which the Edwards is the business part, we're only really looking at the Edwards, but we include the Trinity in this model. So we have these different units, and you see that up in this area it's unconfined. There's no hydraulic communication between adjoining watersheds. You get a little bit deeper in the section, and they start to become confined. So when you get down at the bottom end of these watersheds, you may have some communication between adjoining watersheds. So we're going to be looking at the Devils again, and for the most part, we can consider this a separate hydraulic entity from the other watersheds in the Edwards Trinity. So here's another map of it. We see the watershed up in this area. It drains from the north down to the south. This is a semi-arid area, gets somewhere between 15 20 inches of rain per year, so it doesn't get a lot of recharge. And it's a carbonate karst aquifer, so there's a lot of solutional features that have formed in this limestone over geologic time. But it's a real complicated system. Now, some of the complications that I had to address in this setting will be different than if you were to apply it elsewhere where you have surface water, groundwater. Some of the challenges are a little more difficult, namely that you have a karst system. On the other hand, we find that this is mostly a gaining river, so that eases some of the other complications that we might have otherwise encountered. So we've been working on this for 4 years, and it's taken us quite some time to get to where we are. And a good part of this was just getting a correct conceptualization of the groundwater regime. And an extension of that is the groundwater surface water regime. So if you've been out in this area, it's a large watershed, goes for almost 100 miles from north to south. You get up in these upper reaches, and that riverbed is dry all the time with the exception of some gully washers. It's just dry all the time. Conversely, you get down south, and you always have live water in the lower reach of this river, no matter how severe the drought. It's a real intriguing system. So how is this much water conveyed through this arid desert landscape? If you put this in broader context, somewhere 250 to 300,000 acre-feet of water is discharged out of the Devils into Amistad Reservoir every year. That's a considerable amount of water. And because there's no conservation district in Val Verde County, it's contentious. A lot of people are looking at this water. So it's important that they get their models correct when they're making decisions that are going to impact how they address these some of the challenges they're facing. So if you've been around this area, for the most part what you see are these dry tablelands, and then you have these incised river channels. But if you're going along, Sonora's up here, Juneau's down here, Comstock's down further south. If you drive along this road, you'll come around a bend and you'll see one of the largest pivots that I've ever seen. It has 18 segments. And it's a cornfield out in this area used to support cattle. And it pumps upwards of 2,000 gallons a minute, which is, it was unheard of when I first saw this out in this area. And we looked at this a little more closely, and we mined the Texas Water Development Board database on well information. There are about 2,200 wells in the watershed. 750 or so had some indication of capacity. And capacity, I'm not talking about any kind of aquifer test. It was just simply how much water can these wells pump. And it's a little hard to see, but the reds and the yellows are the higher capacity wells. The greens and the blues are lower capacity. And what you'll see if you look at this a little closer is that all the high capacity wells are lined along surface water channels. And these wells are bedrock wells. They are not alluvial wells. There's no alluvium to speak of in these channels in this watershed. So these are bedrock wells, but the capacity of the wells that are aligned along the rivers all have large capacity. Some 1,000, 2,000, 3,000 gallons per minute out in this desert area, but they're all aligned along the tributaries. And these are those data mapped up, plotted up on this graph. And so you see that the closer you are to the channels, the greater the capacity of the pumps. So why is that? Well, if you look back in some of the technical literature, there's some work done by a couple fellows, Woodruff and Abbott, back to the 70s and 80s, and they really understood what was going on. And what they said was that you have this limestone that's been exhumed over 2 geologic episodes, and as it was raised up relative to the adjoining areas, you had mildly acidic rainwater falling on this plateau, And over time, over geologic time, that mildly acidic rainwater would funnel down to wherever the rivers started, and over time slowly erode away that area. So it's all concentrated along those riverbeds, and over time they not only eroded out the riverbeds, but they enhanced the permeability of the rock along the channels. And that's why those wells that are in the bedrock are so prolific when they're closer to the river channels than away from the channels. You go up in those mesas, and you're lucky to get 5 or 10 gallons a minute. You're down near the tributaries, and you can get 1,000 gallons a minute. And it's because of this mechanism. And so, some people have challenged me on this in the past, and they said, well, it's just because no one has a reason to put a big well up there. And I said, well, you're right, but show me one well up in the mesas that has high capacity, and then I'll have to change my conceptualization, and I haven't seen that yet. So how's it conceptualized? This is just a graphic to give you a sense of how we view the watershed. It's a sponge with pipes. So the rock is a sponge, and these preferential flow paths are pipes. So it just depends where you put a well. If it's along a tributary, near a pipe, if you can get high capacity. If you're up in these mesas, you get low capacity. And going back to that map with all the high capacity wells, that's what we've seen. So this is a conceptualization. We came up with it a few years ago. Since that time, we've tried to gather other data that would either support or refute this conceptualization. So one thing we did was geophysical surveys. We went out and ran electrical resistivity across these tributaries to see if we could see any evidence of the subsurface that would indicate there's a preferential flow path. Well, in electrical resistivity geophysical surveys, what you're measuring is the electrical properties of the subsurface. And rock like limestone or sediments like sands and gravels are electrically resistive. Other materials like silts and clays and shales are conductive. So it's a really good tool for pointing this out. One of the biggest challenges in resistivity is looking at karst systems, because a karst feature can be either conductive or resistive. And what we saw in this area, this is down at Dolan Falls. We ran a transect across the river, and what we saw is we have this conductive zone here. And what we say is that that is a potential indicator of a preferential flow path. We don't know if that's a single large cave, if it's just a bunch of honeycombed rock or whatever, but it has increased permeability relative to the host rock. There's also been a dye tracer test that was conducted by Jim Polonis and the Sutton County Underground Water Conservation District. Now, it was a preliminary test. This is up in Sonora, but they put it in the ground, and it was traveling at a half a mile a day, thereabouts. That is an indication of a karst conduit. Water that goes through a sandstone aquifer or a matrix is going to go, tens of feet a year, and a conduit that can go a mile a day. And so this is an indication in the headwaters, way up in the headwaters, that there's karst. So you're not going to have karst up here and not karst down there. You don't have conduits form and then stop. When a karst feature forms, it continues. So we've done gain-loss measurements to better understand the system. And so TCEQ conducted a gain-loss study back in 2006, and a few years ago, a number of us went out and replicated this survey, and what we found is that river is continuously gaining as you go downstream. And so that's a little bit different than some other systems. There was one little area up near Baker's Crossing where there's a little bit of gain, and they picked that up in 2006, and we saw it when we did it. But other than that, that's a completely gaining system. And I'll come back to that, why that's so important. We looked at groundwater chemistry. Now, we did some work for Sutton County up here, and it sort of piqued our interest. And what you see is over here we have TDS and bicarbonate on the right, and you see that the chemistry of the naturally occurring water tends to mimic where the suspected conduits are. That kind of makes sense, but what is counterintuitive is that you have higher TDS and higher bicarbonate concentrations where the conduits are. You would think that'd be fresher. So we don't fully understand the mechanism there, but the trends are clear. that the water chemistry supports the fact that there are some, there's something aligned with these conduits, or with these tributaries. So how do we model this? Well, we had a earlier attempt at this that didn't do very well, and I'll show you the results that were not terribly comforting. And so we went in, and in this case, we added these discrete features in blue and green. The blue had slightly higher permeability than the green. So we put these in, and we used a software package called ModFlow to develop a finite element model. We put 3 layers in it, the Edwards, 2 in one in the upper Glen Rose, lower Glen Rose, and we had all the surface and everything. And we worked on this for a year and a half or so, and our target to show that we were doing this right was whether we could predict the outflow from the river, since it's all a gaining stream where it discharges to Amistad Reservoir. And we really don't care, because this is a groundwater model, whether we were capturing the high flows during these storm events, but we had to accurately replicate flow during low flow conditions. And down here you see we didn't do it. Our model is the blue, and this is the total flow down at Pafford Crossing, just above where Devil's River goes into Amistad Reservoir. We didn't get it. We just did not get it. So we moved on, and we accommodated our groundwater model by adding a surface water component. And we added the surface water model for the sole purpose of determining what the recharge is. So we ran, the surface water model, and that guided us on whether the recharge was distributed over wide areas, focused in the channels. We let the surface water model dictate that. So if you look at a karst system, it's complicated. So this is, in one respect, where taking on this problem, this case study was more challenging than perhaps others where you don't have karst systems. And you see that you have these conduits that are these preferential flow paths that are aligned with the tributaries. You have precipitation. Maybe there's recharge that's distributed. It's over the mesas. It may be focused in these channels here, or what. It's just a real bugaboo trying to understand that part of it. Understand recharge in these models is the key. And so, if you look at some of the regulatory challenges as I start out, you have surface water here, groundwater here. In Texas, they stay separate. So TCEQ oversees the surface water. They use something called a WAM. Groundwater is overseen by Texas Water Development Board. They use GAMS, and they do not talk to each other. Okay, they're separate models. They're not integrated. They're not coupled. So we couldn't use those models as we tried to look at this problem. So once we tried to couple these models, we started encountering some very challenging technical problems. One was just in the timing of this, because surface water is very fast. You can get a spike in the surface water, from a rain event that lasts for minutes or hours. Groundwater, on the other hand, goes for months, years. And you have to run these models for a long period of time. So you just can't put in a very short, minute or whatever time step into this model and expect it to run efficiently. So there was a real challenge in handling this. So talk a little bit about the surface water. One thing that helps us here is that now there's very high resolution, high quality precipitation data. It's collected by NexRad system, it's radar. It's available going back about almost 15 years now. The resolution is pretty much what you want. We use 4 kilometers by 4 kilometers, and you can just see there are 3 examples of 3 events, and you can see how fine the resolution is. And so, this is important because this is going that surface water model, and then the surface water model is converting, this precipitation into the recharge that goes into the groundwater model. So the way we calibrated the surface water model was to take 6 month-long surface water models and run those separately. And once we got some values that made sense, then we put it into one larger model. So we had 6 smaller models, and there was 1 large event, 2 moderate events, and 3 small events, because we wanted to be able to capture all ends of this. You know, we just didn't want to capture the large events because the smaller events are important too, because you get recharge from all these things. So we were able to come up with a consensus on the properties that went into the model, and so we did a long-term calibration, and what we have here is a precipitation that's just for illustration purposes. This is averaged over the entire county. You see that over here in the green is, I believe, the modeled, and the purple is the measured. This is discharge down at Pafford Crossing, once again where Devil's River discharges in the Amistad Reservoir. So did a pretty good job. You know, I could show you some earlier ones where it was horrible. We didn't have any replication. We weren't capturing the dynamic of, you know, how fast this water was going through the system. But this is where we got to by the end. So this is what comes out of the surface water model. You know, we have this information that comes out of the surface water model. This is our recharge into the groundwater model. So we didn't just take the same groundwater model that we had in that first try. The first try, it was fee flow, finite element. So we went to something called mod flow, USG, unstructured grid. We used that, and we made it 2 layers, just the Edwards and the Trinity. And we increased the resolution and the number of conduits. So we used, you know, we went back and looked at some of the theory of speleogenesis, which is the generation of karst features, and some of the science behind that, and we came up with this. So if you recall that first model of how we had the pipes, the conduits, you know, this is what we went to, and it mimics the tributaries of the surface water. We don't have any information say it doesn't. You know, maybe it varies somewhat. And just taking that a little bit further, it's possible that the groundwater capture area, you know, maybe not exactly the same as surface water. We don't know, so we assume they're both the same. We assume the features in the surface are the same as the features in the subsurface. And so you can see the improvement in the resolution where we went from here to here. So now we've added the surface water, we've improved the groundwater, and we've modeled the system. So this is where we are now. So we feel much better about capturing the system. So the blue is our model, and that brown is the recorded, and you can see that we're doing a better job of capturing this. Now, you know, there's still a little bit more work to do, but we feel we're capturing the essence of this flow system. And you know, once again, we don't care if we can't capture that surface flow because we're not looking at that. What we want to do is be able to have a model, have a tool that we can look at water resource management scenarios. What happens if you put in a pumping regime? What happens if you go into a drought? You know, how does this impact surface flow that goes out of this basin down into the Amistad Reservoir? So this is just comparing where we were about 2 years ago and where we are now. So one of the scenarios, we haven't had a lot of opportunity to do the scenario testing, but we did put in a hypothetical well field somewhere around Juneau, and we said that it's pumping over a relatively focused area because it's going to be focused. If they put something in, it's going to be focused along the river because it makes no sense putting it spread out in this type of flow regime. And you know, we pumped it at 8,000 GPM up in this area. And what we see is that it's pretty much a proportional decrease in surface water. The groundwater and surface water are a intricately coupled regime. What you do in groundwater up in this regime has a direct impact on what happens to the surface water coming out. And so what we saw, and this goes back to what I was talking about a little bit earlier about the gaining system. What we were really impressed with this system was how well it replicated where the springs are in the watershed. And that's because once again, it's an unconfined system. So from really high precipitation times when you're getting a lot of recharge to low, you're only changing the groundwater level by, you know, parts of a foot or a foot or so. But because of the way the springs are in the watershed, you know, by changing the water level maybe by a foot, you're moving the springs maybe, you know, 5 or 10 miles in the watershed. And that's just the way the model is. It's an unconfined system, and it's highly sensitive on the topography of the watershed. And so one of the improvements would be to go out there and get just a much higher resolution river channel where the springs are. And then you could really fine tune this. But that's kind of what we see. And you also see that the springs tend to be back where the rivers cut back up into the dip of the rocks because they go a little bit deeper and they're going to intersect, these preferential flow paths a little bit more. And so, I'm right at the end of the talk, but what we see, we look back at pre-development times, and we see that it predicts that there are springs farther upstream than they are now. And there's a book by a guy named Deeren talking about the Devil's River that's really good. And what he says is back in the 1800s and 1850s, when there were these wagon trains and cattle drives going across Texas, the last place that they would water up would be a place called Beaver Lake on Devil's River, and that even during a drought that occurred in 1850, there was always water in that lake. So they would water up there because they had 3 days without water. That lake bed is still there. They water skied in that lake until the 50s and 60s. Now you go there, it's a dry lake bed, and there's that boat is still in there, but there's no water. And so if you put in pumping, that we can only estimate what the pumping is because they're not metered, and we don't know how much water is being taken out for fracking and the like. But if you take some reasonable amount of water out, we see that those springs migrate from about where Beaver Lake is down to where they are now, which is Hudspeth or Pecan Springs. So the model is really good about getting close to this. And then lastly, what we do is we add that additional well field, and what it causes the springs to migrate further downstream. So that sort of sums up what I came to present, and I can go over this, but pretty much that first point, the topography of the system is the key ingredient that we didn't appreciate early on. And so by having an unconfined system and getting the topography right, you're almost there. And the hydraulic properties that you give to the subsurface, to the conduits and the matrix, are secondary. You can make them almost what you want, as long as they're reasonable, and you're going to get good results. And what we saw is that the development that's occurred in the upper watershed, that's up in Schlager, Crockett, and Sutton counties, although it may be less than 10,000 acre-feet per year, and maybe closer to 5 acre-feet per year, is sufficient to have caused the headwaters to migrate about 10 miles downstream. So, and the groundwater reduces the base flow by some proportional amount. So I'll just go on, and I'd like to acknowledge the folks that have funded this. We went to a number of sources over the past 4 years, and most particularly the Devil's River Conservancy has funded this last part, and we're very appreciative of that. So with that, I don't know if there's any time for any.
That's all the time we have.
Okay.
Will you be around this
Yes,
afternoon?
sir.
If you got any questions, I encourage you to look Ron up this afternoon, and we'll move on to our next presentation. Thank you all.